13.8 billion years ago, everything began. Space itself erupted from a state so hot and dense that our mathematics simply stops working. The temperature reached 10 to the 32nd power Kelvin. The entire observable universe fit inside something smaller than a single proton. We can trace this history backward with extraordinary precision. We can follow the expansion through every epoch, every phase transition, every moment when forces split apart and matter crystallized from pure energy. We can push all the way back to within 10 to the negative 43rd seconds of the beginning, and then we hit a wall. What caused the Big Bang? If it created space and time themselves, then asking what came before might be like asking what lies north of the North Pole. The question itself may have no meaning, yet physicists have spent decades searching for answers anyway. What they have found is stranger than any creation myth ever written. The universe now spans 93 billion light-years across. It contains structures so vast that light takes hundreds of millions of years to cross them, and all of it emerged from that single incomprehensible instant when nothing became everything. The moment before remains hidden. Our equations break down completely at that boundary. General relativity fails. Quantum mechanics offers hints but no certainty. The origin of existence itself sits just beyond the reach of human knowledge. If you enjoy what comes next, consider subscribing and leaving a like. We begin now. Before we go any further, we need to correct something. There is an image in your mind right now. You can probably see it clearly. A massive explosion, matter and energy flying outward in all directions, debris scattering into the darkness of empty space, a cosmic bomb detonating at some specific point, sending everything racing away from ground zero. That image is wrong. This is the part that trips people up, myself included when I first learned it. We're so used to explosions in movies, fireworks in the sky, things flying outward from a center. But the Big Bang wasn't like that at all. It's genuinely hard to picture, and that's okay. The Big Bang was not an explosion in space. It was the expansion of space itself. There is a difference, and that difference changes everything about how we must understand cosmic origins. Matter did not fly outward into some pre-existing void. There was no void waiting to be filled. There was no outside. The fabric of space-time itself came into being and stretched, carrying matter along as it grew. Picture a balloon, not yet inflated, just limp rubber in your hands. Take a marker and draw dots all over its surface. Scatter them randomly. These dots represent galaxies. Now begin to inflate the balloon. Watch what happens to the dots as the rubber stretches. Every dot moves away from every other dot. The distances between all of them increase. But here is what matters. No single dot is at the center of the expansion. If you were a tiny creature living on one of those dots, looking around at your neighbors, you would see them all retreating from you in every direction. You might conclude that you are at the center of everything, that all the other dots are fleeing from your location. But a creature on any other dot would observe the exact same thing. From every point on the balloon's surface, all other points appear to be moving away. Everyone thinks they are at the center. Everyone is right. Everyone is also wrong. The dots are not moving through the surface of the balloon. This is crucial. They are not sliding across the rubber, traveling from one location to another. The rubber itself is growing. The surface is stretching. The dots are simply being carried along for the ride. They stay in the same spot on the balloon. The spot itself just gets farther from all the other spots. Consider what this means for edges. A creature living on that balloon's surface, able to move only along the rubber, would never find an edge. The surface curves back on itself. There is no boundary, no wall, no place where the balloon ends. The surface is finite but unbounded. It has a definite size, yet no edge to bump into. The same is true for our universe. There is no center to expand from. There is no edge to expand into. The fabric of space-time stretches everywhere at once. Every point in the cosmos is equally the center of the expansion, which means no point is special at all. We are not at the center of the universe. Neither is anyone else. The question of where the center is has no answer, because the question makes no sense. This reframing matters. If you imagine an explosion, you imagine a before and an after, an inside and an outside, a center and a periphery. You imagine matter moving through space. None of that applies here. Space itself is the thing that changes. Galaxies are not racing through the cosmos. They are mostly sitting still while the cosmos itself gets larger. The name does not help us. Big Bang sounds like an explosion. It sounds violent and localized and sudden. The term actually came from someone who hated the entire idea. In 1949, a British astronomer named Fred Hoyle gave a BBC radio interview. Hoyle preferred a different model, an eternal universe with no beginning and no end. He found the notion of a cosmic origin point philosophically distasteful, so when describing the competing theory, he called it the Big Bang. He meant it mockingly. He wanted the name to sound ridiculous, to evoke something cartoonish and implausible. The public loved it. The phrase was catchy and memorable. It stuck. The most successful cosmological model in human history is named after an insult from someone who rejected it. Hoyle spent the rest of his life opposing the theory, even as evidence mounted against his preferred alternative. The universe has no obligation to match our aesthetic preferences. The theoretical foundation for this stretching model was laid decades before anyone called it the Big Bang. In 1915, Albert Einstein published his theory of general relativity. It described gravity not as a force pulling objects together, but as the curvature of space-time itself. Mass bends the fabric of reality. Objects follow those curves. What we experience as gravitational attraction is actually geometry. 7 years later, in 1922, a Russian mathematician named Alexander Friedmann worked through Einstein's equations and found something unexpected. The math allowed for a universe that was not static. Space could be dynamic. It could expand or contract. The fabric could stretch or compress over time. Einstein himself had missed this possibility. He had assumed the cosmos was eternal and unchanging, even adding an extra term to his equations to prevent them from predicting motion. Friedmann showed that motion was not only possible but natural. The equations did not require a static universe. They permitted a dynamic one. Space could grow. We now have overwhelming evidence that it does. We can see it happening. Every distant galaxy retreats from us, and the farther away a galaxy sits, the faster it appears to recede. This is not because galaxies are flying through space at tremendous speeds. It is because the space between us and them keeps growing. If this stretching is real, if the fabric of space-time has been expanding since the beginning, then we should be able to find traces of that growth written in light. We should be able to measure the stretch directly, and we can. How do we know any of this happened? The universe does not keep a written record. There are no documents from 13 billion years ago, no fossils from before the Earth existed, no witnesses who can testify about the first moments of everything. And yet, we claim to know what conditions were like billions of years before our planet formed. That seems impossible. The answer lies in something so fundamental we rarely stop to consider it. Light moves. It travels from one place to another, and it takes time to make that journey. Light is fast, extraordinarily fast by any human measure. It crosses about 300,000 kilometers every single second. In miles, that is roughly 186,000 per second. At that speed, you could circle the entire Earth more than 7 times in the space of a heartbeat. Nothing we have ever built comes close to matching it. Nothing in the universe travels faster, but fast is not the same as instant. Light still needs time to cross distances, and in the vastness of space, those distances are staggering. Consider the Sun. It sits at the center of our solar system, flooding the Earth with warmth and light. But the sunlight reaching your eyes right now is not current. It left the Sun's surface about 8 minutes and 20 seconds ago. That light began its journey before you started reading this paragraph. You are not seeing the Sun as it is. You are seeing it as it was. This creates a strange consequence. If the Sun were to suddenly vanish right now, simply blink out of existence, we would have no idea. For over 8 minutes, we would continue bathing in the light of a star that no longer existed. The sky would look normal. The warmth would feel unchanged. We would be living in the afterglow of something already gone. When we look at objects in space, We are not seeing the present. We cannot. The light carrying that information has not arrived yet. Every observation is an observation of the past. Picture what this means across greater distances. 1 light year equals about 9.5 trillion kilometers, roughly 6 trillion miles. That is the distance light travels in an entire year of continuous motion. Not a convenient unit of measurement, but a record of time itself. The nearest star system to our Sun is called Proxima Centauri. It sits about 4.2 light years away. When you look at that star, you are seeing it as it was 4.2 years ago. Whatever is happening there right now, we will not know about for more than 4 years. The present moment of Proxima Centauri is invisible to us. Telescopes are literal time machines. This is not poetry or exaggeration, but simple physics. When you look at the moon on a clear night, you see it as it was 1.3 seconds ago. When you look at the sun through a proper filter, you see it as it was 8 minutes ago. The Andromeda galaxy sits about 2.5 million light years from Earth. When you look at it, the light entering your eyes left that galaxy when early human ancestors were first learning to walk upright on the African plains. Those photons have been traveling through the void longer than our species has existed. You are looking at a ghost from before humanity began. Consider this. By observing objects at progressively greater distances, we are flipping through a photo album of cosmic history. Each image comes from a different era. Each glimpse reveals a different chapter. The farther we look, the older the picture. Modern telescopes can observe galaxies sitting 10 billion light years away. When we look at them, we see them as they were 10 billion years ago. The Earth did not exist yet. Our sun had not ignited. The atoms that would become your body were scattered across space in gas clouds that had not yet collapsed into stars. We are witnessing a universe that predates everything we know. This is how cosmology works. Distance becomes time. The deep universe is the ancient universe. Every photograph of a distant galaxy is a photograph of the past. Here is something stranger still. We can never see the universe as it currently is. The present moment of the cosmos is fundamentally unobservable. Even looking at your own hand involves light that left your skin a tiny fraction of a second ago. You have never seen the present. Nobody has. We are always looking at ghosts. The farther back we look, the closer we get to the beginning. If we push our observations to the extreme limit, we should be able to see the universe in its earliest stages. We should be able to witness the cosmos as it was shortly after everything began, a hot, dense state where space was still young. There is a limit to how far back we can see. Light from before a certain point cannot reach us, not because it is too far away, but because the universe itself was different. The conditions prevented light from traveling freely, but we can get close. We can observe something ancient enough to tell us what the early cosmos looked like. That observation exists. It surrounds us from every direction in the sky. But before we can understand what it shows, we need to understand something else. We need to grasp the evidence that tells us the universe is expanding in the first place. We need to understand how we know that space itself is stretching. How do we know that space is stretching? What evidence tells us the universe is expanding? The answer lives in light itself. Light travels as a wave. Different wavelengths create different colors. Red light has the longest wavelength our eyes can detect. Violet light has the shortest. Between them stretches the entire rainbow, each color corresponding to a specific wavelength of electromagnetic energy. When you look at starlight through a prism, you see this rainbow stretched out, but hidden within that spectrum are dark lines. These are absorption lines, fingerprints left by elements in the star's atmosphere. Hydrogen leaves its mark at specific wavelengths, helium at others. Every element creates a unique pattern. These patterns never change. Hydrogen always absorbs light at the same wavelengths in every laboratory on Earth. They are cosmic barcodes, reliable and consistent across the universe. Or, at least, they should be. In 1912, an astronomer named Vesto Slipher began measuring the light from spiral nebulae. These were fuzzy patches in the night sky whose nature remained unclear. Some thought they were clouds of gas within our own galaxy. Others suspected they might be entire galaxies themselves, island universes beyond our own. Slipher pointed his telescope at these nebulae and captured their light. He found the familiar fingerprints of hydrogen and other elements. But something was wrong. The patterns had shifted. The dark lines appeared in slightly different positions than they should have. By 1917, Slipher had measured 25 spiral nebulae. Nearly all of them showed the same peculiar shift. The absorption lines had moved toward the red end of the spectrum. The wavelengths had stretched. Consider an ambulance racing down a street, siren wailing. As it approaches you, the sound waves compress together. The pitch rises higher. As it passes and moves away, the sound waves stretch apart. The pitch drops lower. This is the Doppler effect. Motion changes the wavelength of the signal. Light behaves the same way. When a light source moves away from you, the waves stretch out, shifting toward red. When it approaches, the waves compress, shifting toward violet. Slipher's red-shifted nebulae appeared to be moving away from Earth, almost all of them, moving away in nearly every direction. In 1927, a Belgian priest and physicist named Georges Lemaitre proposed something radical. Perhaps the universe itself was expanding. Perhaps everything had emerged from what he called a primeval atom, a single point from which all of existence had grown. Few took him seriously at the time. 2 years later, Edwin Hubble changed everything. Hubble had access to the 100-inch telescope at Mount Wilson Observatory in California, the largest telescope in the world at that time. He turned it toward those same spiral nebulae and measured their distances using certain variable stars as cosmic yardsticks. What he found was stunning. The farther away a galaxy sat, the faster it appeared to be receding. This was not random motion. This was a pattern, a law. Hubble's law states that the velocity of a galaxy's recession equals a constant multiplied by its distance. Double the distance, double the recession speed. Triple the distance, triple the speed. The relationship held for every galaxy he measured. But here is what makes this profound. The galaxies are not flying apart like shrapnel from an explosion. They are not racing through space away from some central point. Something else is happening. Space itself is stretching. The redshift Slipher and Hubble observed is not the same as the ambulance siren. That siren changes pitch because the ambulance moves through the air. Galaxies are not moving through space in that way. Instead, the fabric of space is expanding while light travels through it. Picture light leaving a distant galaxy billions of years ago. As that light journeys toward us, space stretches beneath it. The light wave rides on expanding fabric. Over billions of years, the wave itself gets stretched. By the time it reaches our telescopes, its wavelength has grown longer, redder. This is cosmological redshift. It is the universe itself leaving its signature on ancient light. Every distant galaxy shows this effect. The further away we look, the more the light has been stretched, the more the universe has expanded during that light's journey. This is not theory. This is measurement. This is light arriving at our instruments with its wavelength altered by the expansion of space over cosmic time. The universe is growing. It has been growing since the beginning, expanding and cooling from a state of unimaginable density. Here is where the mathematics becomes breathtaking. If the universe is expanding, then it was smaller in the past. Run the expansion backward in time, like rewinding a film. Galaxies draw closer together. Space contracts. The density increases. The temperature rises. Keep rewinding. Further back, the universe grows hotter, denser, smaller. Every galaxy in every direction converges toward the same point. How far back can you rewind? When did the expansion start? Hubble's law gives us a clock. If we know how fast galaxies are receding and how far away they are, we can calculate when they would have all been in the same place, when the expansion began, when everything started. The answer is approximately 13.8 billion years ago. This simple technique, measuring recession speeds and distances, running the math backward, gives us the age of everything, the birthday of the cosmos, the moment when space began its endless stretching. That number has been confirmed by completely independent methods, different observations, different physics, different measurements. They all converge on the same answer, 13.8 billion years. The universe has a measurable age, and we have calculated it by watching light stretch. Think about what this means. By studying how light changes as it crosses the cosmos, we have read the history of space itself. We have counted the years since creation, not through mythology or philosophy, but through the language of physics, written in starlight. The expansion reveals something else. If the universe was denser and hotter in the past, then long ago it must have been incredibly hot, a sea of energy where particles collided constantly, a furnace that filled all of space. If that primordial heat existed, it should have left a signature. A trace of that ancient fire should still be detectable. As the universe expanded and cooled, that energy would have stretched along with space. Its wavelength would have grown longer over billions of years, shifting from visible light to something cooler. If the expansion model is correct, this leftover glow should surround us from every direction. It should be everywhere we look, the afterglow of creation, stretched by billions of years of cosmic expansion into a faint whisper of radiation. This prediction existed for decades before anyone detected it. The theory demanded that such radiation must exist. The universe had an obligation to provide evidence of its own fiery birth. That evidence was found. It changed cosmology forever. That evidence was found by accident. Two engineers trying to fix a broken antenna stumbled onto the oldest light in existence. It happened in 1964. Arno Penzias and Robert Wilson worked at Bell Labs in Holmdel, New Jersey. They were communications engineers, not cosmologists. Their job involved a special horn antenna, a giant metal funnel designed to pick up signals from early satellites. The antenna was sensitive, too sensitive. It detected a persistent hiss of microwave noise that should not have been there. They tried everything to eliminate it. They rebuilt electrical connections. They checked for interference from nearby cities. They pointed the antenna in different directions. The noise remained constant. It came from every part of the sky equally, day or night, summer or winter. The signal never changed. Then they noticed something inside the antenna. Pigeons had been nesting in the horn. Droppings covered the interior surface. Penzias and Wilson climbed inside and scraped the antenna clean, removing what they politely called a white dielectric material. They trapped the pigeons and released them far away. The birds returned. They trapped them again. Eventually, the pigeons did not come back. The noise persisted. Imagine cleaning pigeon droppings off your equipment, only to discover you have accidentally found the echo of creation itself. That is exactly what happened. The hiss was not coming from the antenna. It was not coming from the atmosphere or from any source on Earth. It was coming from the universe, from everywhere in the sky, from every direction simultaneously. Meanwhile, just 60 kilometers away at Princeton University, a team of physicists was actively searching for exactly this signal. Robert Dicker, Jim Peebles, Peter Roll, and David Wilkinson knew what to look for. They understood the prediction. That prediction dated back to 1948. Ralph Alpha and Robert Herman had calculated that if the universe began in a hot, dense state, residual heat should still exist today. They estimated it would have cooled to approximately 5 Kelvin. That is 5 degrees above absolute zero, colder than anything on Earth, colder than the space between planets. But not zero, not nothing, a faint warmth left over from the beginning. When the Princeton team learned about the mysterious noise plaguing the Bell Labs antenna, the connection was immediate. Penzias and Wilson had found it. They had detected the leftover heat from the birth of the universe. They were not looking for it. They did not know what it was, but they had measured it precisely. Both teams published their findings together. Penzias and Wilson described the observations. The Princeton group explained what those observations meant. In 1978, Penzias and Wilson received the Nobel Prize in Physics. The cosmic microwave background had been confirmed. To understand what they found, you need to picture the early universe, not as empty space, but as a plasma, a soup of charged particles so hot and so dense that light could not travel through it. Consider trying to walk through an extremely dense fog. You can only see a short distance in any direction. Light scatters constantly off the fog droplets. It cannot travel far before being redirected. You are surrounded by whiteness. The fog is everywhere, and you cannot see beyond it. The early universe was like this, but for light itself. Photons bounced endlessly off free electrons in a hot, dense state. The universe was opaque. Light existed, but it was trapped. It could not escape the plasma. Every photon that formed was immediately absorbed and re-emitted in a random direction. The cosmos was filled with light that could go nowhere. This continued for hundreds of thousands of years. Then, something changed. The universe had been cooling since the beginning. As space expanded, the temperature dropped. Around 380,000 years after everything started, the universe reached approximately 3,000 Kelvin. Still hot by any earthly standard, hotter than molten lava, but cool enough for something remarkable to happen. At that temperature, electrons could finally slow down. They could be captured by atomic nuclei. Protons grabbed electrons and became hydrogen atoms. Helium nuclei grabbed electrons and became helium atoms. This process is called recombination. Free particles became bound together into neutral atoms. Neutral atoms do not scatter light the way free electrons do. The fog cleared. Suddenly, for the first time in cosmic history, light could travel freely. Photons that had been bouncing for hundreds of thousands of years were released. They began their journey across the universe. They have been traveling ever since. That light is what Penzias and Wilson detected. Those photons left the plasma 380,000 years after the universe began. They have been crossing space for nearly the entire age of everything. When they finally reach our instruments, they carry information from that moment of clearing, the last surface they touched before flying free. The original temperature of that light was 3,000 Kelvin, but the universe has expanded enormously since then. Space has stretched. The wavelength of that ancient light has stretched along with it. What was once visible light, glowing orange and red, has been pulled into the microwave portion of the spectrum. Its temperature now measures 2.725 Kelvin, almost at absolute zero, a faint whisper of what it once was. The uniformity of this signal is striking. Measure the cosmic microwave background from any direction in the sky, north, south, east, west, above the plane of our galaxy or below it. The temperature is the same everywhere to extraordinary precision. Variations exist, but they are tiny, 1 part in 100,000. That means if the average temperature is approximately 2.7 Kelvin, the differences between hot spots and cold spots are measured in millionths of a degree. The early universe was almost perfectly smooth, almost perfectly uniform. The hot, dense state that existed before recombination had the same temperature everywhere, give or take almost nothing. We have mapped these tiny variations with increasing precision. A satellite called COBE, launched in 1989, made the first detailed measurements. WMAP followed in 2001 with sharper resolution. The Planck satellite, launched in 2009, produced the most detailed picture yet. Each mission revealed the same pattern: subtle ripples in the temperature, seeds that would eventually grow into galaxies and clusters of galaxies. But at that early moment, just hints, just whispers of structure to come. The cosmic microwave background is not just evidence for the expansion. It is a photograph, the oldest photograph possible. Light cannot bring us images from earlier because before recombination, there was no free light to carry images. The universe was a wall of scattering plasma. The CMB is that wall, seen from the outside. After we emerged from it, we can see all the way back to 380,000 years after the beginning. But the first 380,000 years remain hidden behind a wall of light we cannot penetrate. The universe was opaque then. What happened in those first moments? We must infer from theory and from the evidence that survived. And what we think happened is stranger than we might expect. The CMB tells us the conditions at recombination, the temperature, the density, the slight variations that seeded cosmic structure. But it cannot show us the moments before, the era when atoms did not exist, when even protons and neutrons had not yet formed, when the universe was so hot that matter itself behaved differently than anything we experience today. Those first moments left their own evidence. not in light, because light could not escape, but in something else, in the composition of the universe itself, in the proportions of elements that existed before stars ever ignited. If the hot, dense state was real, it should have acted as a furnace, a cosmic forge that built the first atomic nuclei from raw particles. The recipe it followed should match what we observe today. So let us rewind further, past the moment when light first escaped, past those first 380,000 years, back to when the universe was not just hot, but impossibly hot, a furnace so intense that atoms could not exist, a cauldron where the very building blocks of matter were being assembled for the first time. Picture a kitchen, not an ordinary kitchen, but one operating under conditions no chef has ever faced. The oven is set to 10 billion degrees. Every ingredient you try to combine gets vaporized the instant you place it inside. You cannot bake anything because the heat destroys whatever you create. The universe, 1 second after its beginning, was exactly this kind of kitchen. Too hot for anything complex to survive. Protons existed, neutrons existed, but the moment they tried to combine into something larger, the environment tore them apart. At this temperature, protons outnumbered neutrons by roughly 7 to 1. This ratio mattered. It would determine everything that came next. The proportions of ingredients available would set the final recipe forever. The universe was expanding and cooling. Every moment, the temperature dropped. The oven was slowly dialing itself down, but it was still too hot. Protons and neutrons occasionally collided and fused into deuterium. Deuterium is the simplest compound nucleus, one proton bound to one neutron. It should have been the first step toward building heavier elements, but deuterium is fragile. In that blazing environment, high-energy photons struck every deuterium nucleus the instant it formed, shattered it, scattered the pieces back into the cosmic soup. This was the deuterium bottleneck, a temperature gate that refused to open. You cannot proceed to the next step of the recipe if your first ingredient keeps getting destroyed. The universe had to wait, not for long by human standards, but in cosmic terms, an eternity of failed attempts. The clock kept running, expanding and cooling, always expanding and cooling. At 3 minutes and 46 seconds after the beginning, the temperature had fallen to roughly 900 million degrees. Still, unimaginably hot by any earthly measure, but cool enough, finally cool enough. Deuterium could survive. The gate opened. What happened next was fast, astonishingly fast. Once deuterium stopped being destroyed, it became the gateway to everything else. Deuterium nuclei fused with more protons to form helium-3. Helium-3 combined with other particles to form helium-4. The recipe was finally proceeding. Ingredients that had been impossible to keep stable were now assembling themselves at tremendous speed. The cosmic kitchen, after minutes of frustration, was suddenly working. But there was a problem. The same expansion that allowed the process to begin was also ending it. The universe kept expanding and cooling. By 20 minutes after the beginning, the temperature had dropped too far. The particles were moving too slowly. They could no longer overcome the electromagnetic repulsion that keeps nuclei apart. Fusion stopped. The oven had cooled below the threshold needed to cook anything else. The window had closed. 17 minutes. That was all the time the universe had to build its first elements. Everything created in that narrow window was locked in. The proportions were fixed forever. 75% hydrogen by mass, 25% helium-4, trace amounts of deuterium and lithium, 7. Almost nothing else. No carbon, no oxygen, no iron, no gold. None of the heavy elements that make up your body, your planet, the ground beneath you. Those would come later, forged in the hearts of stars that did not yet exist. The universe in those first minutes could only build the lightest nuclei. It ran out of time before it could build anything heavier. Here is where the prediction meets reality. If the hot, dense beginning was real, if this cosmic kitchen actually operated the way physics demands, then we should find these exact proportions when we look at the oldest, most pristine material in the universe. Gas clouds that have never been inside a star, regions untouched by stellar fusion for billions of years. We looked, we measured, the proportions match. 75% hydrogen, 25% helium, trace deuterium, trace lithium. Exactly what the theory predicted. Not approximately, not roughly, exactly. The recipe written in the first 20 minutes of existence is still legible today, stamped into the composition of ancient matter across the cosmos. This is not a coincidence. This is confirmation. 3 independent lines of evidence now point to the same conclusion. The expansion of space, the afterglow of cooling radiation, the abundance of light elements. All 3 tell the same story. All 3 demand the same beginning. But here is something that might surprise you. All of this, every atom we have discussed, every proton and neutron and electron, represents almost nothing. The ordinary matter that makes up stars and planets and people accounts for only 4 to 5% of everything in the universe. We are a minority, a tiny fraction of the cosmic total. For millennia, we assumed we were the dominant form of existence, that the stuff we could see and touch and measure was all there was. We were wrong. The vast majority of the universe is made of something else entirely. Dark matter we cannot see, dark energy we cannot touch. Together they account for over 95% of everything. We are floating in an ocean of invisible forces, a thin scattering of ordinary atoms in a cosmos dominated by mysteries we have barely begun to understand. The evidence from nucleosynthesis is solid. The predictions match observations with remarkable precision. But nucleosynthesis began 1 second after the beginning. What happened in that first second remains hidden. The kitchen was already operating when our evidence begins. We know what was cooked. We know the proportions. But we do not yet know who lit the flame. To answer that question, we must venture into the first fractions of a second, into temperatures and densities where the rules of physics themselves begin to blur, where protons and neutrons had not yet formed, where the forces of nature behaved differently than anything we experience today. The evidence from those earliest moments is written in a different language entirely. That different language, the language of particles so fundamental they make atoms look like cities, of temperatures so extreme they have no comparison in the universe today, of time sliced so thin it loses all meaning. We trace the evidence back to 1 second after the beginning, the cosmic kitchen where helium was forged. But 1 second is an eternity compared to what we must examine now. The first fractions of a second contain more physics, more transformation, more raw violence than all the billions of years that followed. Let us rewind further, much further, the Planck epoch, the absolute beginning of time as we can describe it, from 0 to 10 to the negative 43 seconds. That number deserves explanation. Write a decimal point, then 42 zeros, then a 1. That is how small this time interval was. A trillionth of a trillionth of a trillionth of a trillionth of a second. Shorter than any process that has ever occurred anywhere in the universe since. During this moment, everything that would become the cosmos existed in a state we cannot properly describe. The temperature reached 10 to the 32 Kelvin. To feel how extreme that is, consider that the core of our sun burns at about 15 million degrees. The Planck temperature was 100 trillion times hotter than that. At this heat, in this density, the 4 fundamental forces of nature did not exist separately. Gravity, electromagnetism, the strong nuclear force, the weak nuclear force. All 4 were unified into a single force, one interaction governing everything. The fabric of space-time itself was twisted and distorted beyond recognition. Actually, let me be more precise here. When I say the universe was smaller than a proton, that is our best extrapolation from current physics. But the truth is our mathematics breaks down at the Planck scale. We are really describing what our equations suggest should have happened, not what we can directly observe or verify. We are at the edge of knowing. General relativity describes gravity beautifully at large scales. Quantum mechanics describes particles beautifully at small scales. But at the Planck epoch, you need both. Gravity was as strong as the quantum forces, and we have no theory that unifies them. Our equations return nonsense, infinities where there should be answers. Our physics fails. After that first inconceivably brief moment, things began to change. The grand unification epoch lasted from 10 to the negative 43 seconds until 10 to the negative 36 seconds. During this window, gravity peeled away from the other forces. It became its own thing, warping the fabric of space-time independently. But the remaining three forces, electromagnetism, the strong force, and the weak force, stayed merged together. The universe was still unimaginably hot, still smaller than anything you could visualize. But already it was becoming more complex. Already the unified whole was fracturing into distinct pieces. By 10 to the negative 12 seconds, the temperature had dropped to about 10 to the 15 Kelvin. That is 1,000,000 billion degrees. The electro-weak force split apart. Electromagnetism went one way. The weak nuclear force went another. The strong force had already separated earlier. For the first time, the universe had all four distinct forces we recognize today. This entire sequence of separation happened in less time than light takes to cross a single proton. At 10 to the negative 6 seconds, around 1/1,000,000th of a second, the universe entered what physicists call the quark epoch. The temperature was roughly 1,000,000,000,000 degrees, 1,000,000,000,000. At this heat, quarks could not bind together. They swam freely in a sea of gluons, the particles that normally hold them tight within protons and neutrons. This was quark-gluon plasma, pure energy and fundamental particles churning together in a hot, dense state, unlike anything since. No protons yet, no neutrons, just the raw ingredients, unable to combine because the fabric of space-time was still stretching too violently, the temperature too extreme for anything stable to form. And within this chaos, something happened that determined everything: matter and antimatter. In the equations of physics, they are mirror images. Every particle has an antiparticle with opposite charge. When they meet, they annihilate each other completely. Both vanish. Pure energy remains. This is not theory. We create antimatter in laboratories every day. We watch it annihilate. In the early universe, both matter and antimatter were created in nearly equal amounts. Nearly, not quite. Imagine a cosmic battlefield where matter and antimatter are locked in total annihilation. For every billion soldiers on each side, nearly all are destroyed in mutual combat. Matter meets antimatter, gone. Energy. Matter meets antimatter, gone. Energy. 1,000,000,000 on one side, 1,000,000,000 on the other. Mutual destruction. But there was a tiny asymmetry. One extra grain of sand on one side of an otherwise perfectly balanced scale. For every billion antimatter particles, there were 1,000,000,001 matter particles. One extra, that is all. When the annihilation finished, almost everything was gone, converted to energy, light, radiation. The vast majority of matter and antimatter that the universe created destroyed each other completely. 1,000,000,000 annihilated. One survived. That survivor is you and the stars, and every atom in every galaxy in the observable universe. We are the one in 1,000,000,000 leftovers of a war of total destruction. The planets, the mountains, the oceans, your heartbeat, all of it traces back to that tiny excess, that fraction of a fraction. Here is the surprise. We do not know why there was more matter than antimatter. The laws of physics, as we understand them, are almost perfectly symmetric. If you write down the equations governing particles and forces, they treat matter and antimatter as equals. Nothing in our current physics explains why one side should outnumber the other. Something violated that symmetry. Some process broke the balance. This is called baryogenesis, the creation of baryons, the family of particles that includes protons and neutrons. It remains one of the great unsolved problems in physics. If that violation had not occurred, if the numbers had been perfectly equal, matter and antimatter would have annihilated completely. The universe would contain nothing but cooling radiation. No galaxies, no stars, no planets, no life, nothing that could ever look back and ask questions. The fact that you exist is evidence that something we do not understand happened in the first fractions of a second. We have traced the story back through nucleosynthesis, through the quark epoch, through the separation of forces, to the wall at 10 to the negative 43 seconds. Each step backward reveals more extreme conditions, higher temperatures, denser states, stranger physics. But even this successful account has problems. The universe we observe today is remarkably uniform. The same temperature in every direction. The same distribution of matter whether we look left or right, up or down. Distant regions that could never have been in contact with each other somehow look identical. The hot, dense state we have described cannot explain this uniformity, not on its own. Something else must have happened, something that stretched and smoothed the early cosmos faster than light itself, something that violated our usual understanding of how quickly things can change. The standard model of the Big Bang works remarkably well. It explains the cosmic background radiation. It predicts the exact proportions of hydrogen and helium. It traces the separation of forces and the emergence of matter from energy. But it has problems. Deep, structural problems that the model alone cannot answer. Consider this. The universe we observe is almost perfectly flat, not curved like a sphere, not saddle-shaped like a horse's seat. Flat. Euclidean geometry works. Parallel lines stay parallel forever. The angles of a triangle add up to exactly 180 degrees. This seems ordinary until you realize how unlikely it is. General relativity tells us that matter bends space. A universe with stuff in it should curve. And here is the strange part. The flatness we observe requires the initial density of the universe to have been tuned with absurd precision. 1 part in 10 to the 60th power. That is a 1 followed by 60 zeros. Imagine trying to balance a pencil on its tip so perfectly that it stands for 14 billion years without falling. The slightest deviation in either direction at the beginning, and the universe either collapses back on itself immediately or expands so fast that nothing ever forms. No galaxies, no stars, no planets, no you. This is called the flatness problem, and nobody could explain it. Then there is the horizon problem. Look in any direction, and the universe has the same temperature, the same density, the same structure. Regions on opposite sides of the sky appear identical, but those regions are separated by tens of billions of light years. And here is what should bother you. They have never been in contact. Light has not had time to travel between them. Information has not had time to travel between them. Nothing has. So how do they know to look the same? How did they coordinate their temperature to match within 1 part in 100,000 if they have never communicated? The standard Big Bang model offers no answer. It simply assumes the universe started uniform everywhere. That is not an explanation. That is a starting condition chosen specifically to match what we see. Then, there is a third puzzle. Grand, unified theories predict that the early universe should have created magnetic monopoles. These are hypothetical particles with only one magnetic pole, north without south, or south without north. They should exist in enormous quantities. Every detector ever built should be tripping over them constantly, yet we have never found a single one. Where did they go? In 1980, a physicist named Alan Guth proposed a radical solution. All 3 problems could be solved by a single idea, a brief period of exponential expansion in the first moments of existence. He called it cosmic inflation. The timing is almost impossible to comprehend. Inflation occurred between 10 to the negative 36th seconds and 10 to the negative 32nd seconds after the beginning. That entire event lasted for a duration so short that no human clock could ever measure it. Less than a trillionth of a trillionth of a trillionth of a second. During that vanishingly brief window, the universe expanded by a factor of at least 10 to the 26th power. That is a 1, followed by 26 zeros. A region smaller than the smallest particle you can imagine, inflated to roughly the size of a grapefruit. Not over millions of years. Not over thousands of years. Not over seconds. Over a time span so short, it makes the blink of an eye seem like an eternity. Picture a wrinkled balloon, perhaps a deflated party balloon with creases and folds across its surface. Stretch it to enormous size. Keep stretching. The wrinkles flatten, the creases disappear. Eventually, any small patch of that surface looks perfectly smooth, perfectly flat. You cannot detect the original curvature anymore because it has been stretched beyond recognition. Inflation did something far more extreme. It took whatever curvature existed in the early universe and stretched it so dramatically that the observable cosmos became geometrically flat. Not because the universe started flat, but because any initial curvature was diluted into invisibility. Consider standing on the Earth. The ground beneath your feet appears flat. You cannot perceive the planet's curve because you are too small. The Earth's surface extends too far in every direction. Imagine the Earth inflated to 1 trillion times its current size. The curvature would become even more imperceptible. Inflation performed this trick with the entire fabric of space, expanding reality by a factor so large it defies every comparison. What was curved became flat. What was wrinkled became smooth. The horizon problem dissolves under inflation's solution. Those distant regions that appear identical but seem never to have communicated, they were once neighbors. Before inflation, the entire observable universe fit within a space small enough for light to cross easily, small enough for temperatures to equalize, small enough for information to flow freely in every direction. Everything we can see today was once in intimate contact. Then, inflation stretched that tiny patch to cosmic scales. Regions that could once communicate were suddenly separated by distances too vast to ever reconnect. The magnetic monopoles disappear through the same mechanism. Grand unified theories predict they formed before inflation began. Any monopoles that existed were then diluted across a volume suddenly expanded by a factor of 10 to the 78, spread so thin across so much space that the odds of finding even one in our observable universe dropped to effectively zero. They are not gone. They are simply lost in an ocean of emptiness so vast we will never encounter them. 3 problems, 1 solution. Inflation explains why the universe is flat without requiring impossible fine-tuning. It explains why distant regions match without requiring them to communicate across impossible distances. It explains why monopoles vanish without requiring them never to have existed. But here is something stranger. Inflation may not have stopped. At least, not everywhere. The version of inflation that ended in our region of space, allowing matter and energy to form, allowing galaxies and stars and planets to eventually emerge. That ending may have been local. In other regions, beyond anything we can ever observe, inflation may continue forever. Space expanding exponentially, doubling and doubling again. Occasionally, random quantum fluctuations cause inflation to end in small patches. Those patches become pocket universes, places where the physics might differ, where the constants take different values, where entirely separate cosmic histories unfold. This is called eternal inflation, and it leads to a conclusion that sounds like science fiction but emerges directly from the mathematics. Our universe may be one bubble in an infinite foam, one island of calm in an endlessly churning sea, new universes spawning forever in regions we can never detect, never visit, never know. The expansion that inflation triggered did not vanish. It simply handed off to a gentler process. After inflation ended, the universe continued expanding and cooling. The extreme temperatures of the earliest moments began their long decline. Energy converted to matter. Particles formed and combined. The cosmic story we have traced from nucleosynthesis forward began in earnest. But the expansion itself carries inflation's fingerprint. The smoothness we observe, the flatness we measure, the absence of monopolies we cannot find. All of these trace back to that vanishing moment when reality stretched faster than light itself, when a speck smaller than anything imaginable became the foundation of everything we know. Inflation lasted for less time than any human process has ever measured, yet its consequences shaped the structure of the cosmos. Every galaxy you will ever see, every star that will ever burn, every atom in your body, all of it owes its existence to that brief, violent stretching at the dawn of time. The physics behind this transformation deserves a closer look. Before the universe could build anything, It needed raw material, and that material came from somewhere unexpected. It came from energy itself. In 1905, a patent clerk in Switzerland published a paper that would reshape our understanding of reality. Albert Einstein showed that mass and energy are not separate things. They are two faces of the same coin, two ways of describing a single underlying substance. His famous equation links them with a simple relationship. Energy equals mass multiplied by the speed of light, squared. That last part matters enormously. The speed of light is already a staggering number, nearly 300,000 kilometers every second. But squared, it becomes something else entirely, roughly 90 quadrillion. Written out, that would be a 9 followed by 16 zeros. This means a tiny speck of matter contains a reservoir of energy almost beyond comprehension. We see this relationship in nuclear reactions, in the heart of a star, in the flash of an atomic weapon. A little bit of matter converts to energy, and the result shakes worlds. But Einstein's equation works both ways. If mass can become energy, then energy can become mass. In the furnace of the early cosmos, this reverse process dominated everything. Picture something strange, a kind of freezing, but nothing like what you know. When water cools, it transforms. Liquid becomes solid. Disordered molecules lock into rigid crystal structures. The cold brings order. The cold brings form. In the newborn universe, cooling worked differently. The cosmos began as something almost impossible to describe. Pure, radiant energy. No particles as we understand them. No protons. No electrons. Just a seething ocean of light and force, hotter than anything that has existed since. As this ocean cooled, it began to condense. Energy crystallized into substance. The universe froze out of pure fire, like morning dew condensing from humid air. Each drop of dew is water that was always there, suspended invisibly in the atmosphere. The cooling simply allowed it to become visible, to take form, to exist as something you could touch. This is what happened to matter itself. The ingredients were always present, encoded in the blazing energy of the earliest moments. Temperature held them dissolved. As the heat faded, they precipitated out. Reality crystallized. The process unfolded in stages. Each cooling threshold released new kinds of particles into existence. The heaviest appeared first, when temperatures were most extreme. Particles with names that sound like they belong in science fiction. Exotic quarks, massive bosons, things that exist for the briefest instants before decaying into lighter offspring. As the temperature dropped further, these heavy particles could no longer form. The energy required to create them exceeded what random collisions could provide. One by one, they disappeared from the cosmic inventory, frozen out not by cold, but by insufficient heat. Think about it this way. When the universe blazed at its hottest, photons carried enough energy that when two collided, they could spontaneously produce a particle and its antiparticle partner. The energy transformed into mass, conjuring matter from light itself, but this worked only above certain temperature thresholds. Below that threshold, the reaction stopped. Photons still collided, but they no longer carried enough punch to birth new particles. The universe had grown too cold for that particular act of creation. The sequence continued. Heavier particles froze out first, then came lighter ones. Layer by layer, the zoo of exotic matter simplified. By the time the cosmos had cooled enough for nucleosynthesis to begin, only the familiar cast remained: protons, neutrons, electrons, and the photons themselves, still outnumbering matter particles by more than 1 billion to 1. This freezing process left the universe with its basic ingredients, the same ingredients that would later form stars, planets, oceans, and eventually you. All of it condensed from energy during those furious early moments. Here is something that might surprise you. Mass is stored energy. This is not a metaphor, not a poetic way of speaking. It is literally true, and we can demonstrate it in ordinary situations. Lift a book from a table, hold it above the surface. You have just added gravitational potential energy to that book, and because energy and mass are equivalent, that book now weighs more than it did on the table. The difference is unmeasurably small, smaller than any scale could ever detect, perhaps a billionth of a gram, but it is real. Heat a pot of water. The hotter water is ever so slightly more massive than the cool water was. Not because you added any atoms, you added energy, and energy has weight. This equivalence seems abstract at everyday scales because the speed of light squared is such an enormous number. The mass changes from adding ordinary amounts of energy are invisibly tiny. But in particle accelerators, where we smash particles together at velocities approaching light speed, the effect becomes dramatic. Collide two protons with enough violence, and the energy of their collision can birth entirely new particles. Particles that did not exist before. Impact. Particles heavier than either proton that collided. The energy converts to mass, just as it did in the first moments of creation. Scientists have verified this thousands of times. We create matter from energy in laboratories on Earth. The early universe simply did it on a cosmic scale, with temperatures and energies we cannot hope to replicate. The conversion was not perfectly efficient. Most photons remained photons. Most energy stayed as light, but enough condensed into matter to seed everything that followed. Every galaxy that would form, every star that would burn, every planet that would coalesce from cosmic debris, all traced back to this fundamental transformation. Energy became matter when conditions allowed. Matter remained stable when conditions no longer favored its dissolution back into light. The cooling universe locked in its gains, step by step, threshold by threshold. By the time of recombination, when atoms first formed and light broke free to become the cosmic microwave background, this process had long since completed. The matter content of the universe was set. Hydrogen dominated, helium came second, and traces of heavier elements would have to wait for stellar forges yet to ignite. But the foundation was laid. Energy had crystallized into the building blocks of everything. The fire had frozen into form, and the universe, still expanding, still cooling, carried within it all the matter it would ever need to build worlds. The matter content was set. The light had broken free, and then the universe went dark. Not dark like night, not dark like a room with the lights off, dark in a way that nothing in human experience can match. For the next several 100 million years, there was nothing to see. No stars burned, no galaxies glowed. The cosmic microwave background had already departed on its endless journey, its light stretching longer and longer as space itself continued growing. What had been visible radiation shifted into the infrared, then further, into wavelengths no eye could ever detect. The universe had entered its dark ages. Picture the scene, a vast expanse of hydrogen and helium gas, cooling steadily as it spreads thinner through the expanding void. The temperature dropping toward 10 Kelvin. That is negative 263 degrees Celsius. Colder than any natural place in our solar system today. Colder than the space between stars in the modern universe, which is actually warmed slightly by starlight that did not yet exist. The universe, expanding and cooling, had reached its coldest era, and it would stay this way for an almost incomprehensible span of time. 300 million years, perhaps 500 million. We are not certain of the exact duration, but consider what that means. The entire history of anatomically modern humans spans roughly 300,000 years. Every civilization we have ever built, every empire that has risen and fallen, every thought ever recorded, fits within a tiny fraction of that time. The dark ages of the cosmos lasted 1,000 times longer than our entire species has existed. And during all of it, nothing visible was happening. Nothing visible. But that does not mean nothing important. This is the part that gets me. Hundreds of millions of years of absolute darkness, of patient gravitational assembly in the cold and the silence. No eyes to see, no light to see by, just hydrogen slowly falling into invisible wells of dark matter. There is something almost meditative about it, this longest night before the first dawn. Imagine sitting in a completely dark room. You cannot see anything, you cannot hear anything, but you know, somehow, that somewhere in that darkness, furniture is being assembled, slowly, piece by piece. You cannot watch it happen. You cannot check on the progress. You can only wait, trusting that when the lights finally come on, everything will be in place. That is what gravity was doing during the Dark Ages, building the foundations of everything we see today. The ordinary matter, the hydrogen and helium gas, could not collapse on its own. It had spent the previous 380,000 years locked in a tight embrace with light, pushed outward by radiation pressure as fast as gravity could pull it inward. Even after recombination released that grip, the gas was still too hot, too energetic to simply fall together. It needed help. Dark matter provided that help. Dark matter makes up approximately 27% of everything in the universe. We have never seen it directly. We cannot touch it, capture it, or detect it except through its gravitational influence. It does not emit light. It does not absorb light. It passes through ordinary matter like a ghost walking through walls. The only force it responds to is gravity. And gravity had been working on dark matter from the very beginning. During the era when ordinary matter was still trapped in its dance with photons, dark matter was already clumping. It felt no radiation pressure. Nothing pushed it back. It could begin gathering immediately after the universe formed, pulled together by its own mutual attraction. By the time recombination occurred, dark matter had already built structures throughout the cosmos. Dark matter halos, astronomers call them, invisible spheres of this ghostly substance, concentrated around overdense regions that had been seeded during the earliest moments. These halos acted as gravitational scaffolding, like the steel framework of a building waiting for the walls and windows to be added. The structure was there. It just needed something to fill it. The ordinary matter that would become stars and galaxies was drawn in slowly, like fog settling into valleys. Hydrogen gas drifted toward the centers of dark matter halos, pulled by gravity it could not see or understand. The process was agonizingly gradual. Gravity is the weakest of all fundamental forces. Over short distances and short timescales, it is almost negligible compared to the electromagnetic force or the nuclear forces that hold atoms together. But gravity has one advantage. It never gives up. Over millions of years, then tens of millions, then hundreds of millions, gravity kept pulling. The gas fell inward, compressed slightly, heated up from the compression. This heating actually slowed the collapse, because hot gas wants to expand. The gas had to radiate away that energy, cooling itself down before it could fall further. This radiative cooling process takes time, enormous amounts of time. The Dark Ages were a cosmic waiting room where nothing visible was happening, but everything important was being arranged. Gravity was doing its patient, silent work in the darkness, building the scaffolding, gathering the raw materials, preparing for ignition. We know almost nothing about this era from direct observation, and that is one of the strangest facts in all of astronomy. Look at the cosmic microwave background, and you are seeing the universe as it was 380,000 years after the beginning. Turn a powerful telescope toward the most distant galaxies, and you can observe objects from when the universe was perhaps 500 million years old. We have images of both bookends, but the chapter in between remains essentially invisible. The Dark Ages are the longest era of cosmic development we cannot see. There were no luminous sources to produce light. The only radiation present was the fading echo of the cosmic microwave background, stretched beyond detection. If you had been floating in that void with human eyes, you would have seen nothing. Perfect, absolute blackness in every direction. Astronomers are now attempting to pierce this darkness for the first time, not with visible light, not even with infrared, with radio waves. Specifically, they are searching for a faint signal at a wavelength of 21 centimeters. Neutral hydrogen atoms, the kind that filled the Dark Ages universe, occasionally emit radiation at this precise wavelength. It happens when the electron orbiting a hydrogen nucleus spontaneously flips its spin orientation. The signal is extraordinarily weak. Any individual atom might go millions of years without emitting a single 21 centimeter photon. But there was an unimaginable amount of hydrogen during the Dark Ages. Collectively, that gas should have produced a detectable glow, a glow that has been traveling toward us for over 13 billion years, stretched by expansion to wavelengths of several meters. Specialized radio telescopes are being constructed to find this signal. If they succeed, we will have our first direct window into the Dark Ages. We will see the universe as it was during that long, cold night before the first sunrise. Until then, we can only model what happened, run simulations on supercomputers, watch digital universes evolve in fast forward, dark matter clumping, gas falling, density increasing in certain regions while other regions emptied out. The simulations show a web-like structure forming, filaments of matter connecting at nodes, vast empty voids growing between them. This cosmic web is the scaffolding the universe built during its longest night. The densest nodes in that web were where things would happen first, where gravity had gathered the most dark matter, the most ordinary gas, where compression had progressed furthest, where, after hundreds of millions of years of silent assembly, the temperature and pressure at the center of certain gas clouds would finally cross a critical threshold. The darkness could not last forever. Somewhere, in one of those dense pockets, hydrogen atoms were being squeezed together more tightly than anywhere else in the universe. The temperature was rising, not from external heat, from the pressure of all that falling gas. Eventually, inevitably, the core temperature would reach the point where hydrogen nuclei could overcome their electrical repulsion. They would fuse. They would release energy. A star would ignite. The first dawn was coming, and then there was light. After hundreds of millions of years of perfect darkness, something changed. Deep within one of those dense pockets of collapsing gas, the pressure became too great. The temperature climbed too high, and hydrogen nuclei, stripped of their electrons, slammed together with enough force to merge. The first star turned on, not gently, not gradually. It erupted into existence with a ferocity the universe had never known. This was no ordinary star. It was a monster. The first generation of stars were unlike anything that exists today. Astronomers call them population 3 stars, and they were born from pristine gas, pure hydrogen and helium. No carbon, no oxygen, no iron, nothing heavier than those two primordial elements forged in the first moments of creation. This absence changed everything about how they formed. In the universe we know today, heavier elements act as cooling agents in collapsing gas clouds. They radiate energy away efficiently, allowing the gas to collapse into smaller, denser regions. Without these elements, the first gas clouds could not cool as effectively. They remained hotter as they fell inward. The result was that the collapsing regions grew much larger before they finally ignited. Population 3 stars were giants on a scale that defies imagination. The smallest of them contained perhaps 30 times the mass of our Sun. Many were hundreds of times more massive, and the largest may have exceeded 100,000 solar masses. Our Sun is a modest yellow star, middle-aged and stable. These primordial furnaces were something else entirely. They burned with surface temperatures that made our Sun look cold by comparison. Picture a firework that illuminates the entire sky. The burst lasts less than a heartbeat, but for that instant, everything is light. That is what population 3 stars were to the cosmos. They blazed with the radiance of millions of suns combined into single points of searing brilliance, and they died almost as quickly as they appeared. Their lifetimes were measured in just a few million years. A few million years sounds like a long time. It is not. The universe would persist for nearly 14 billion years. These stars lived for perhaps 3 million of those years. That ratio is staggering. If the entire history of the cosmos were compressed into a single year, population 3 stars would exist for roughly 8 hours total. They were here, and then they were gone. Cosmic eye blinks, brilliant and brief. Their deaths matched their lives in violence. When a star exhausts its fuel, gravity wins. The core collapses. What happens next depends on mass. For stars like our Sun, the end is gentle. A slow expansion into a red giant, then a quiet fade into a white dwarf. For massive stars, the collapse triggers an explosion, a supernova. For the most extreme population 3 stars, something stranger occurred. In the cores of these monsters, the temperature climbed so high that photons themselves began converting into particle pairs, matter and antimatter created from pure light. This robbed the core of pressure support. The star began collapsing faster, which raised the temperature further, which created more pairs, which accelerated the collapse. The entire star detonated in what physicists call a pair instability supernova. These were not ordinary supernovae. When a typical massive star explodes, it leaves behind a remnant, a neutron star or a black hole. Some core survives. But in pair instability explosions, the detonation was so complete, so absolute, that nothing remained. The entire star was converted into expanding debris. No neutron star, no black hole, just a shell of gas racing outward through the void. And inside that gas was something precious, something new. Those first stars, in their brief lives, had done something the early universe never could. They had built heavier elements. Inside their crushing cores, hydrogen fused into helium, helium into carbon, carbon into oxygen, oxygen into neon and magnesium and silicon and sulfur and calcium and iron. The entire periodic table up to iron was forged in those stellar furnaces. When they exploded, they scattered these elements across space. Carbon atoms that had not existed anywhere in the universe were suddenly drifting through the void. Oxygen molecules, iron nuclei, the raw materials for rocky planets and liquid water and organic chemistry. These elements seeded the surrounding hydrogen gas, mixing with the pristine material that remained. The next generation of stars would be different. With heavier elements now present, the gas could cool more efficiently. Smaller clouds could collapse. Stars could form at more modest masses. These second-generation stars lived longer, billions of years instead of millions. They burned more slowly. Some of them are still shining today, ancient survivors from the universe's earliest epochs. Those first stars died so that everything after them could exist. We have never seen a population 3 star. Not directly. They are entirely theoretical constructs, predicted by the physics of stellar formation, but extinct for over 13 billion years. By the time we build telescopes powerful enough to observe the era when they existed, every single one has already exploded. We are too late. We will always be too late. We know they existed because of what they left behind. The chemical enrichment they created is written into every star that came after. The iron in your blood, the calcium in your bones, the oxygen you are breathing right now, all of it was synthesized in stars. But the first generation of those elements came from population 3 explosions. We are reconstructing a crime scene where the perpetrators vanished 13 billion years before detectives evolved to investigate. The evidence is in the chemistry of ancient stars. Some stars in our galaxy are extraordinarily old. They formed perhaps 12 or 13 billion years ago from gas that had been enriched by only 1 or 2 generations of previous stars. The elemental abundances in these ancient stars carry signatures, specific ratios of elements that match what pair instability supernovae would produce. We cannot see the primordial stars directly, but we can read their fingerprints in the survivors that inherited their ashes. Meanwhile, gravity continued its patient work. Stars did not form in isolation. They formed in clusters. In the densest nodes of the cosmic web, these clusters began to merge. Small proto-galaxies, containing perhaps a few million stars each, fell together under mutual gravitational attraction. Larger structures absorbed smaller ones. The process was hierarchical. Small became medium. Medium became large. Large became the great galactic systems we observe today. This assembly took billions of years. The Milky Way did not form all at once. It grew through cosmic cannibalism. Smaller satellite galaxies fell into our growing system, their stars torn apart and absorbed. This process continues even now. Dwarf galaxies orbit our own, slowly spiraling inward, destined to be consumed. We are still assembling ourselves, still growing, still merging with smaller neighbors. Every galaxy has a similar history. The great spiral galaxies, the massive ellipticals, the irregular dwarfs, all of them built themselves from smaller pieces. Gravity gathered stars into clusters, clusters into proto-galaxies, proto-galaxies into galaxies, galaxies into groups and clusters of galaxies. Structure grew from the bottom up. The cosmic web tightened, filaments of galaxies connected at massive nodes. The darkness had given way to light. Where once there was only cold hydrogen drifting through an invisible scaffolding of dark matter, there were now blazing suns, trillions of them. More stars than grains of sand on all the beaches of Earth, each one a furnace converting hydrogen into heavier elements. Each one continuing the work those first monsters began. The violence created the beauty. Those primordial stars had to die. Their explosive ends seeded the universe with complexity. Without their sacrifice, stars like our Sun could not have formed. Rocky planets could not have coalesced from the solar nebula. The chemistry of life would have remained forever impossible. The cosmos built itself through destruction. Stellar explosions cleared away the old and enriched the new. Gravitational collisions merged smaller structures into larger ones. What seemed like chaos was actually construction. The universe was not simply expanding, it was organizing. It was building complexity from simplicity, structure from uniformity, light from darkness. Billions of years of this process eventually produced the cosmos we now inhabit, a universe filled with billions of galaxies, each galaxy containing billions of stars. Many of those stars orbited by planets, some of those planets made of rock and iron, a few of those rocky worlds sitting at just the right distance from their parent stars, cool enough for liquid water, warm enough to prevent eternal freeze. On at least one such world, something extraordinary happened. But that is getting ahead of the story. For now, what matters is this. The long night ended. The cosmic dawn broke. The first stars burned and died, and in their deaths, they planted the seeds for everything that would follow. We live in a universe that is no longer dark. The universe we now inhabit is no longer dark. Stars blaze in their trillions. Galaxies wheel through the void. But where exactly are we in all of this? Where do we fit within the architecture of everything that exists? Let us write our address, not the street where you live, not your city or your country, something larger, something that stretches across distances so vast they require new ways of thinking about space itself. We begin with Earth, a rocky world orbiting a modest star. That star, our Sun, is one among hundreds of billions in a vast rotating disk of light and dust. We call this disk the Milky Way. The Sun does not sit at its center. We reside in one of its spiral arms, a region known as the Orion Arm. Picture it as a quiet suburb, far from the dense, chaotic downtown of the galactic core, far from the bustling activity where stars crowd together by the millions. The Milky Way itself spans roughly 100,000 light-years from edge to edge. That number means little without context. Light, the fastest thing in existence, would need 100,000 years to cross our galaxy. A beam of light leaving one side today would not reach the other until long after human civilization has either flourished or faded into memory. The disk is thin compared to its width, about 1,000 light-years thick. If our galaxy were the size of a dinner plate, it would be thinner than a sheet of paper. The Sun moves through this disk. It orbits the galactic center, pulled by the combined gravity of all those hundreds of billions of stars. One complete orbit takes approximately 230 million years. Astronomers sometimes call this a cosmic year, a single trip around the galaxy. Consider what that means for our planet. Earth has existed for about 4.5 billion years. In that time, our world has completed perhaps 20 orbits around the galactic center. The dinosaurs went extinct about 66 million years ago, less than 1/3 of a cosmic year in the past. All of human civilization fits within a fraction of a cosmic heartbeat. We measure our lives in decades. The galaxy measures its rotations in hundreds of millions of years. Imagine writing your address on an envelope, first your street, then your city, then your country. Each line represents a larger container holding the one before it. Keep extending that address upward, and it continues to grow. Earth, solar system, Orion Arm, Milky Way. The Milky Way is not alone. It belongs to a gathering of galaxies called the Local Group. Over 50 galaxies cluster together here, bound by mutual gravitational attraction. The Local Group spans roughly 10 million light-years. Our nearest major neighbor is the Andromeda Galaxy, a spiral similar to our own. Andromeda contains perhaps 1 trillion stars. Both galaxies are falling toward each other, destined to merge billions of years from now. Add another line to the address. Earth, Solar System, Orion Arm, Milky Way, Local Group. The local group itself is merely a small neighborhood within a much larger structure. We belong to the Virgo supercluster, a collection of galaxy groups and clusters stretching across 110 million light-years. Thousands of galaxies populate this region. The Virgo cluster, near its center, contains over 1,000 galaxies alone. We orbit somewhere in its outer reaches. But even the Virgo supercluster is not the end. In 2014, astronomers mapped the flow of galaxies across a larger region still. They discovered that the Virgo supercluster is just one lobe of an even greater structure. They named it Laniakea. The word comes from Hawaiian. It means immense heaven. Laniakea contains approximately 100,000 galaxies. It spans 500 million light-years. The Milky Way, our home galaxy with its hundreds of billions of stars, is one among 100,000 similar or larger systems within this single supercluster. Each of those galaxies contains billions of stars, each star potentially surrounded by worlds. Earth, Solar System, Orion Arm, Milky Way, Local Group, Virgo supercluster, Laniakea. Beyond Laniakea, superclusters connect to other superclusters. They form vast filaments and walls. Between these structures lie enormous voids, regions where almost nothing exists, hundreds of millions of light-years of near emptiness. The overall pattern resembles a cosmic web, a foam-like structure where matter concentrates along thin sheets and threads surrounding immense bubbles of void. This brings us to the final line of our address, the observable universe. The observable universe has a diameter of approximately 93 billion light-years, a radius of about 46.5 billion light-years in every direction from Earth. Everything we can see, every galaxy we can photograph, every distant quasar whose light reaches our telescopes, exists within this sphere. Here lies something that seems impossible. The universe is only about 14 billion years old. Light has only had 14 billion years to travel. How can we observe objects nearly 47 billion light-years away? The answer reveals something profound about the nature of space itself. Space has been expanding while the light traveled toward us. Galaxies that emitted light early in cosmic history were much closer to us then. Their light began its journey across a younger, smaller universe. But as that light traveled, space itself stretched. The universe expanded beneath the light's feet, so to speak. By the time that ancient light reaches our telescopes, the galaxies that emitted it have been carried much farther away by the ongoing expansion. We see those galaxies not where they are now, but where they were billions of years ago. They were closer then. They are far more distant now. The light is old news, reporting on conditions that existed long before our sun ever formed. The observable universe is not a snapshot of the present. It is a composite of every moment in cosmic history, layered around us like the rings of a tree. This is our cosmic address, a small, rocky planet orbiting an ordinary star in a quiet arm of a spiral galaxy. That galaxy floating within a cluster of neighbors. That cluster embedded within a supercluster. That supercluster forming one node of an immense heaven. That immense heaven connected to countless others in a web of filaments and voids, all of it expanding, all of it drifting through a darkness that stretches for tens of billions of light-years in every direction. Each level of the address is exponentially larger than the one before. Each step upward reveals how small the previous step truly was. And yet here we are, aware of our place within this structure, able to trace our location across scales that dwarf anything our ancestors could have imagined. We understand so much now, the age of everything, the shape of cosmic structure, the expansion that carries galaxies apart, the ancient light that tells us how the universe looked in its youth. We have mapped our address with remarkable precision, but understanding our place does not mean understanding our origin. We know where we are. We know how old everything is. We know what the universe looked like in its earliest visible moments. What we do not know is how it all began. How it all began. We have spent so much time building toward this question. We have traced the expansion backward. We have listened to the oldest light. We have counted the hydrogen and helium forged in the first minutes. We have followed gravity as it sculpted galaxies and lit the first stars. We have mapped our place in a web of structure that spans tens of billions of light years. And now we arrive at a wall. Everything we have described, every triumph of modern cosmology, runs into a fundamental problem when we push it back far enough. The equations that have served us so well begin to fail. The mathematics that predicted the cosmic microwave background, that explained the abundance of elements, that described the expansion of space itself, all of it breaks down when we approach the very beginning. General relativity is one of the most successful theories in the history of science. It describes how mass curves space, how curved space tells matter how to move. It predicted black holes decades before we photographed one. It predicted gravitational waves a century before we detected them. It explains the bending of starlight, the drift of Mercury's orbit, the ticking of clocks on satellites. It works beautifully across scales from the solar system to the largest structures in the cosmos. But there is a limit. When we run the expansion backward, space contracts, density rises, temperature climbs, push far enough, and everything in the observable universe gets compressed into smaller and smaller volumes. General relativity tells us what happens as this compression continues. It tells us that density approaches infinity, temperature approaches infinity, space itself shrinks toward a point. This is the singularity. In the 1960s and 70s, Stephen Hawking and Roger Penrose developed mathematical proofs. They showed that singularities are not just possible within general relativity. Under certain conditions, they are inevitable. If you accept the equations, you accept the singularity. The math leads there, whether you want it to or not. But a singularity is not a thing. It is not a place you could visit. It is not an object with properties you could measure. A singularity is where the equations stop making sense, where the numbers become infinite, where the theory itself confesses that it cannot describe what is happening. Trying to use general relativity to describe this moment is like trying to use a map that only shows roads to navigate the ocean. The map is excellent for driving. It will get you across continents. It will guide you through mountain passes and across deserts. But the moment you reach the shoreline, the map goes blank. There are no roads on the water. The tool that served you so well has reached the edge of its usefulness. It is not that the ocean does not exist. It is that your map was never designed to describe it. Infinities are nature's way of saying, you have asked a question your theory cannot answer. They are a signal, a red flag, a warning that you have pushed beyond the boundaries of what your mathematics can handle. The equations are not revealing truth. They are revealing their own limitations. This is where we reach the honest limits of what we know. Not what we suspect, not what we calculate, but what we actually know. And the answer is, not much. We have theories, beautiful mathematical structures that might describe what happened, but we cannot test them. We cannot look back past the cosmic microwave background, and we cannot recreate Planck scale conditions in any laboratory. We are reasoning in the dark. The Planck scale marks the boundary. At distances of 10 to the negative 35 meters, lengths so small that a single proton would span them a trillion times over. At timescales of 10 to the negative 43 seconds, intervals so brief that light itself travels less than the width of a Planck length. This is where general relativity loses its grip. This is where something else must take over. But what? We need a theory that combines general relativity with quantum mechanics. A theory of quantum gravity. General relativity describes the very large. Quantum mechanics describes the very small. Both work spectacularly in their own domains, but they speak different languages. They make different assumptions about the nature of reality. Merging them has proven to be one of the hardest problems in all of physics. No complete theory of quantum gravity exists today. There are candidates: loop quantum gravity, string theory, others. Brilliant physicists have devoted their careers to these frameworks, but none has been confirmed by experiment. None has been proven correct. They remain possibilities, not answers. And here is where the question itself becomes strange. We want to know what happened before the Big Bang. The question feels natural. Everything has a cause. Every event has something that preceded it. How could there not be a before? But consider this. General relativity taught us something profound. Space and time are not separate things. They are woven together into a single fabric called space-time. Time is not some external stage on which events unfold. Time is part of the physical universe. It bends, it stretches, it slows near massive objects. If space-time began at the Big Bang, then time itself began at the Big Bang. And if time began there, asking what came before may be like asking what is north of the North Pole. Stand at the North Pole and point north. There is no more north to go. Every direction leads south. The concept of north has reached its limit. It breaks down. It no longer applies. Similarly, if time originated at the singularity, there may be no before. Not because we lack the ability to see it, not because it is hidden behind some barrier, but because the very concept of before stops being meaningful. The question has no answer because the question itself may be physically empty. This is not evasion. This is not mysticism dressed up in scientific language. This is a direct consequence of Einstein's insight that time is physical. If space-time can begin, then so can time. And if time can begin, then there is a point at which asking what came earlier makes no sense. The strangeness deepens. Some physicists now suspect that time itself may be emergent, not fundamental, not woven into the deepest fabric of reality, but arising, somehow, from something more basic. The way temperature emerges from the motion of molecules, the way wetness emerges from collections of water molecules, even though no single molecule is wet. Before the Planck epoch, time as we understand it may not have existed, not hidden, not inaccessible, simply not yet real. We do not know if this is true. We have no way to confirm it, but the mathematics of quantum mechanics offers strange new possibilities. It suggests that the singularity may not be the final word, that there might be ways to describe what happened at the origin without running into infinities, that the wall we have hit might not be a true wall, but merely the edge of what our current tools can see. Quantum mechanics has surprised us before. It revealed that empty space seethes with energy, that particles can tunnel through barriers. That measurement changes what is measured. Perhaps it has one more surprise in store. Perhaps it holds the key to understanding how something came from nothing, or whether nothing ever existed at all. That word, nothing. We use it so casually. The room is empty. The jar is empty. Nothing inside. But quantum mechanics has revealed something strange. True emptiness does not exist. What we call empty space is anything but empty. Picture a pot of water sitting on your stove. From across the kitchen, it looks calm, still, peaceful. But move closer. Press your face near the surface, and you see activity everywhere. Tiny bubbles forming at the bottom, rising through the liquid, breaking at the surface, new ones taking their place, an endless churning that was invisible from a distance. The quantum vacuum is like this pot, except the bubbles are particles, and the churning never stops. What appears to be nothing, when examined at the smallest scales, reveals ceaseless activity, a constant dance of creation and destruction happening everywhere, all the time. This is not metaphor, this is measurement. In 1947, a physicist named Willis Lamb discovered something peculiar about hydrogen atoms. The energy levels of their electrons did not match what theory predicted. They were slightly shifted, off by a tiny amount. The explanation was startling. Virtual particles, popping in and out of existence in the vacuum, were nudging those electrons. Ghosts of particles that exist for only the briefest instant were leaving measurable fingerprints on real atoms. 1 year later, in 1948, another experiment confirmed something equally strange. Two metal plates placed very close together in a vacuum experience a measurable force pushing them toward each other. Nothing touches them. No air, no radiation, just empty space between them. Yet they feel a pull. This is the Casimir effect. The vacuum itself exerts pressure. Empty space pushes. How can emptiness push? How can nothing have energy? The answer lies in a principle first articulated by Werner Heisenberg. Certain pairs of properties cannot both be known with perfect precision at the same time. The more precisely you measure one, the fuzzier the other becomes. Position and momentum, energy and time. There is a fundamental limit to what can be simultaneously determined, not because our instruments are crude, but because the universe itself contains this blur. This uncertainty allows something remarkable. For very brief moments, energy can appear from nowhere. Particles can pop into existence, borrowed against the uncertainty budget, as long as they vanish quickly enough. The shorter they live, the more energy they can briefly possess. These are virtual particles. They are not permanent. They exist in a kind of limbo between being and non-being. The quantum vacuum seethes with such particles, appearing, annihilating, appearing again, everywhere, all the time. In the space between your fingers right now, an invisible storm of creation and destruction is unfolding. So when we ask whether the universe came from nothing, we must first ask what nothing means. The quantum vacuum has properties. It fluctuates. It contains energy. It pushes and pulls. Philosophers debate whether this counts as true nothingness. If our universe emerged from a quantum vacuum, did it emerge from nothing, or did it emerge from something? This is not just wordplay. This is a genuine puzzle at the heart of cosmology. But there is a way the universe could have emerged without cheating, without requiring energy to appear from nowhere and stay. Consider a simple idea. What if the total energy of the universe is exactly zero? Think of a perfectly balanced accounting ledger. You can create $1 million of debt if you simultaneously create $1 million of assets. Write one on the left side, one on the right. The net is zero. You have created something from nothing in a very real sense. Assets and liabilities that did not exist before now exist, but they cancel perfectly. The universe may work the same way. All the matter we see, the stars, the galaxies, the atoms in your body, represents positive energy. Mass is energy. Light is energy. Motion is energy. Add it all up and you get an enormous positive number. But gravity is different. Gravitational potential energy is negative. Two masses pulling toward each other represent a kind of energy debt. The closer they fall, the deeper the debt becomes. If you add up all the positive mass energy in the universe, then subtract all the negative gravitational energy, the total might be exactly zero. The cosmic books may have always been balanced, even at the moment of creation. If this is true, then the universe did not violate any conservation law by appearing. It did not require energy from outside. It simply separated zero into positive and negative pieces. The ultimate free lunch. Something for nothing, because the something and the nothing still cancel. We do not know if this accounting is exact. The calculation is difficult, but it remains a genuine possibility. The universe may have emerged not in spite of the laws of physics, but because of them. There is another approach to the mystery, one that does not ask what came before, but what came through. Loop quantum gravity offers a radical reimagining of space itself. In Einstein's vision, the fabric of space-time is smooth, continuous. You can always divide it into smaller pieces. There is no smallest unit, no final atom of space. But loop quantum gravity disagrees. It proposes that space-time is quantized, grainy, made of discrete units at the smallest scales. Imagine a finely woven cloth. From across the room, it looks smooth, seamless, without texture. But press your eye close enough, and you see individual threads crossing and weaving. The smoothness was an illusion of distance. In this theory, space itself is woven from tiny fundamental loops, individual stitches in the fabric of reality. At scales we can probe, space appears continuous. But at the Planck scale, the threads reveal themselves. Space has atoms, tiny, indivisible units that cannot be divided further. This changes everything about the singularity. In Einstein's equations, the universe contracts toward zero size and infinite density. The mathematics breaks. Division by zero. Infinite quantities appearing where finite answers should be. But if space cannot be compressed below a certain size, infinity never arrives. The contraction stops. The density reaches a maximum, unimaginably extreme, but still finite. And then, something remarkable happens. It bounces. The universe rebounds. What was contracting begins expanding. The hot, dense state we call the Big Bang may not have been the beginning at all. It may have been a transition, a moment when a previous universe, collapsing in on itself, reached its limit and bounced back outward. If this is true, then asking what came before the Big Bang has an answer. Another universe, contracting toward us through time, reaching the bounce point, then expanding into everything we see. And what came before that universe? Perhaps another bounce, another cycle. The cosmos breathing in and out, an endless rhythm of contraction and expansion. Each universe inheriting something from the last, each bounce creating the conditions for the next. We cannot prove this yet. Loop quantum gravity remains unconfirmed by experiment, but the mathematics holds together. The infinities that plague Einstein's equations are tamed. The singularity is replaced by something we can calculate. Whether time truly began, or whether it cycles endlessly, remains unknown. Both possibilities sit within the reach of physics. Both represent genuine scientific hypotheses, not speculation. The question of ultimate origin may have no single answer, or it may have an answer that surprises us. Some physicists have proposed even more radical ideas that our three-dimensional universe floats within a higher dimensional space, that entire worlds could exist alongside ours, invisible, separated by dimensions we cannot perceive. These ideas extend beyond what we have explored tonight. They require us to imagine space with more than 3 dimensions, membranes colliding in the dark, bubble universes inflating from quantum foam, those membranes colliding in the dark, those bubble universes inflating from quantum foam. Let us go there now. Let us enter a realm where space itself has more depth than we can see. For most of the 20th century, physicists described matter as made of tiny points, electrons, quarks, point-like particles with no internal structure, just dots, infinitely small, infinitely concentrated. This worked remarkably well for predicting experiments, but it also created problems. When you calculate what happens at infinitely small scales, infinities keep appearing. The math spirals out of control. String theory offers a different vision. In this framework, the fundamental building blocks of reality are not points. They are strings, tiny filaments of pure energy vibrating at different frequencies. Each vibration pattern corresponds to a different particle. An electron is a string vibrating one way. A quark is the same string vibrating differently, like a violin string producing different notes depending on how it shakes. These strings are unimaginably small, far smaller than anything we have ever measured, far smaller than anything we could measure with current technology. To see one directly, you would need a particle accelerator larger than our solar system, perhaps larger than our galaxy. We will never build such a thing, but the mathematics is precise, and the mathematics demands something unexpected. For the equations to work, for the string vibrations to produce the particles we observe, the universe cannot have just 3 dimensions of space. It must have more. The theory requires 10 or 11 dimensions in total, not 3 spatial dimensions and 1 of time. 10 or 11 altogether. We live our entire lives moving forward and backward, left and right, up and down. 3 directions, 3 dimensions of freedom. String theory says there are 6 or 7 more that we cannot access, cannot perceive, cannot even imagine properly. Where are they? Why do we never bump into them? The answer is that they are compactified, curled up, folded into themselves at scales so impossibly tiny that we pass through them without ever noticing. Every point in the space around you contains these hidden dimensions, wrapped up tighter than anything in human experience. You exist in them right now. You always have, but they are invisible to everything we can do or build or measure. Here is something to sit with. The number of different ways these extra dimensions could be curled up is staggering. About 10 to the 500th power. Write that out. A1 followed by 500 zeros. That number is larger than the number of atoms in our observable universe. Larger by an incomprehensible margin. Each different way of curling produces a different set of physical laws. different particle masses, different forces, different universes. The fabric of space-time, the thing we have been exploring throughout this journey, takes on new meaning here. It is not just curved, as Einstein showed. It is not just quantized, as some theories suggest. In string theory, it is a membrane, a brain, a surface floating through something larger. Picture a two-dimensional sheet of paper. Imagine creatures living on that paper, flat beings with length and width but no height. They can slide across the surface. They can move in any direction along it, but they cannot jump up from it. They cannot perceive the three-dimensional room in which their paper floats. To them, their flat world is everything. The room does not exist. Their entire physics would describe only two dimensions. Their telescopes would see only what exists on the paper, other flat beings, flat stars, if such things made sense. They would have no concept of above or below, no words for it, no mathematics for it. If you tried to explain the room to them, they would struggle. How can there be directions that do not exist? We may be those creatures. Our three-dimensional universe might be a brain, a membrane suspended in a higher dimensional space called the bulk. We can move forward and backward, left and right, up and down, but we cannot step off the brain. We cannot perceive the bulk. Everything we see, every star, every galaxy, every photon of light is confined to this membrane. The higher dimensions are there. We simply cannot reach them. Gravity might be different. Some models suggest that gravity, alone among the forces, can leak into the bulk. This could explain why gravity is so weak compared to other forces. Electromagnetism holds atoms together with ease. Gravity cannot even keep a paperclip stuck to a table. Perhaps gravity is diluted, spreading into dimensions we cannot access. Weakened by the vastness of the bulk, other brains may exist out there, parallel membranes drifting through the same higher dimensional space, invisible to us, perhaps containing their own matter, their own physics, their own observers asking the same questions we ask. And sometimes, according to one model, brains collide. This is the ekpyrotic scenario. The word comes from ancient Greek. It refers to a cosmic fire, a conflagration that destroys and renews. In this picture, our Big Bang was not the beginning of everything. It was a collision. Two brains, drifting slowly through the bulk over vast stretches of time, finally touched. Consider two sheets of paper floating through that three-dimensional room, drifting closer, drifting for eons, then finally, gently, clapping together. From the perspective of creatures on either sheet, what would this look like? Energy appearing everywhere at once, not coming from any direction along the paper, not originating from a point, just suddenly present, everywhere. An explosion of heat and light with no source they can point to, because the source is in a direction they cannot perceive. That is what our Big Bang might have been. Not an explosion from a point, not the beginning of time, just two membranes meeting in a place we cannot imagine. The collision heats both brains to extreme temperatures. Matter and energy flood across the surfaces. The universe enters a hot, dense state. From our perspective, anchored to our brain, it looks exactly like what we call the Big Bang. The same physics follows, the same expansion, the same cooling, the same formation of particles and atoms, and eventually stars. But the implications are different. After the collision, the brains slowly drift apart. They cool, they evolve, and eventually, over timescales we cannot fathom, they drift back together. Another collision, another Big Bang, another cycle. Our universe may be infinitely old, not in the sense that our current expansion has lasted forever. It has not. Everything we measure points to an origin roughly 14 billion years ago. But that origin might not have been the first. There may have been a previous universe, a previous cycle, a brain that existed, evolved, cooled, and then collided to create what we experience as our beginning. And before that cycle, another. And before that, another still. Time itself becomes cyclic in this view, not a line stretching from a beginning to an end, a wheel, turning endlessly, each rotation producing a new universe, each universe eventually giving way to the next. There is something both humbling and comforting in this picture. We are not unique in a troubling way. We are part of something larger, something that has always been happening, something that will continue after our universe grows cold and dark. We cannot prove any of this. Not yet, perhaps not ever. String theory has not been confirmed by experiment. The extra dimensions remain hidden. The brains remain theoretical. We are reasoning from mathematics, not measurement. But the mathematics holds together. The equations work. And if the equations are pointing us somewhere, perhaps we should look. These models share something important with what came before. Loop quantum gravity offered cycles through bounces. String theory offers cycles through collisions. Different paths to the same destination. The universe may have no true beginning, no first moment, only transitions. And if multiple brains exist, drifting through the bulk, then something else follows naturally. We are not alone. Not in the sense of life, though perhaps that too, but in the sense of existence itself. Other universes may float alongside ours right now, separated by dimensions we cannot cross, close enough to touch, in a direction we cannot point to. Other universes may exist alongside ours, not just as a poetic idea, as a consequence of the physics we already accept. Return to inflation for a moment, that brief period of violent expansion that smoothed our cosmos. The energy field that drove it did not have to stop everywhere at once. In fact, the mathematics suggests it could not. Inflation ends in patches, small regions where the energy field decays, where expansion slows, where matter and radiation flood in. Those regions become universes like ours, pocket universes, islands of calm in an ocean that never stops churning. But between those pockets, inflation continues, forever. The space between them stretches faster than light, faster than any signal could cross. Each pocket universe is born, evolves, and ages in complete isolation. No message could ever pass between them. No telescope could ever see across the gap. They are forever separate, forever unreachable. This is eternal inflation, not a theory designed to create multiple universes, a consequence of the same inflation that solved the flatness problem and the horizon problem, the same inflation that left its fingerprints in the cosmic microwave background. Follow the equations and you arrive here, an infinite foam of bubble universes, each one an entire cosmos, most of them completely unlike our own. Here is where it gets stranger. Remember the hidden dimensions, the tiny curled up spaces that might explain why gravity is so weak, why particles have the masses they do. Those dimensions can be folded in many ways, not a few ways, not thousands, not millions, 10 to the power of 500 possible ways. That number is so absurd it is almost funny. If you tried to count to that number, 1 per second, the universe would end countless times over before you finished. It is not a number that means anything to human intuition. It is a number that breaks human intuition and just keeps going. Each way of folding those dimensions produces a different set of physical constants, a different strength for gravity, a different mass for electrons, a different value for the force that holds atoms together. Each pocket universe in the eternal foam might realize a different folding, a different physics, a different chemistry, or no chemistry at all. Universes may form like soap bubbles in an infinite bath, each with its own properties, most hostile to any form of complexity. No stars, no planets, no atoms stable enough to build anything, just energy dissipating into darkness, or collapsing back into nothing before anything interesting can happen. But a rare few might support observers, beings who can look around and ask why the universe seems so hospitable, why the forces balance, why stars burn long enough for planets to form, why chemistry works. This changes how we think about the fine-tuning problem. Look at the constants of our universe, the strong nuclear force that holds protons and neutrons together in atomic nuclei. Change it by just a few percent stronger, and hydrogen cannot exist. All of it fuses immediately. Change it a few percent weaker, and nothing beyond hydrogen can form. No carbon, no oxygen, no us. The electromagnetic force that governs chemistry. Shift it slightly, and electrons cannot orbit nuclei in stable patterns. Atoms do not bond. Molecules never form. The intricate dance of chemistry that makes life possible simply stops. The cosmological constant, the energy of empty space. Theoretical calculations predict it should be vastly larger than what we observe, off by a factor of 10 to the power of 120. That is not a small error. That is the largest mismatch between theory and observation in all of physics. And yet, if empty space had the energy we naively predict, the universe would have torn itself apart before a single galaxy could form. Our existence seems to depend on a razor's edge of precision, numbers tuned to values that allow complexity, allow life, allow minds that can wonder about origins. Before the multiverse, this demanded explanation. Was it chance? Design? Some deeper law we had not yet discovered? The multiverse offers another answer. In an infinite multiverse, asking why our universe supports life is like asking why we find ourselves on a planet with water. We could not exist on a planet without water. Our presence here is not surprising, just selective. A cosmic lottery with infinite tickets guarantees every number will win somewhere. We hold a winning ticket not because we are special, but because we could not hold a losing one, and ask why. Cosmologists have organized these ideas into levels, 4 categories of multiverse, each more expansive than the last. The first level is simple. If space is truly infinite, then every possible arrangement of matter must occur somewhere. Given enough distance, you would eventually find another Earth, another you, not through magic, through statistics applied to infinity. The second level is eternal inflation, pocket universes with different physical constants, different laws, the landscape of possibilities made real across an endless foam of creation. The third level comes from quantum mechanics, the many worlds interpretation. Every quantum measurement splits reality into branches. Every possibility plays out somewhere, not in distant space, in a kind of parallel existence we cannot access. The fourth level is the most radical. Every mathematically consistent structure exists as its own universe. Not just our physics with different constants. All possible physics. All possible mathematics made physical somewhere. Here is something worth sitting with. The multiverse is not a single theory. It is a destination that multiple independent theories seem to reach on their own. Eternal inflation arrives there from cosmology. The string landscape arrives there from particle physics. Quantum mechanics arrives there through its own strange logic. 3 different roads, same destination. That convergence makes some physicists take the multiverse seriously, even though we may never test it directly, even though the other universes are forever beyond our reach. When different frameworks all point the same direction, it might mean something, or it might mean we are all making the same mistake. We cannot know. Not yet. Perhaps not ever. But the possibility remains. An infinite sea of universes, each one complete, each one unknowable to the others, most barren, a few flowering with complexity. And in one of those rare pockets, on a small blue world, creatures look up at the night sky and wonder how they came to be here at all. And from this life raft, we look out at the infinite hostile waters and marvel that we exist at all. There is a name for this realization. Philosophers call it the anthropic principle. It comes in 2 forms. The first, the weaker version, simply observes that we can only find ourselves in a universe compatible with our existence. This is almost a tautology. Of course we observe conditions that allow observers. We could not be here otherwise. The stronger version goes further. It suggests the universe must possess properties that eventually give rise to consciousness. That awareness is not an accident, but somehow woven into the fabric of reality itself. This is more controversial, more mysterious, perhaps more beautiful. Consider where this leaves us. The fine-tuning of physical constants, the precise values that allow stars and planets and minds. These demand explanation. There are only 3 possibilities. The first is chance. We simply got lucky. Against all odds, the cosmic dice rolled in our favor. The second is necessity. Perhaps there is only one way the universe could be, one set of constants, one configuration, and we happen to live in that singular possibility. The third is selection. Countless universes exist with different properties. We find ourselves in one suitable for us because we could not find ourselves anywhere else. Our existence is like finding ourselves on the one life raft in an infinite ocean of hostile seas. We did not survive because the ocean was kind. We survived because we could not have existed in the hostile waters. The ocean is not for us. We are simply in the one small place where we could be, and from this life raft, we can look out at those infinite hostile waters and feel something unexpected, not despair, not insignificance, but gratitude, awe, the quiet recognition that we are here at all. Perhaps the ultimate answer to what caused the beginning is that the question itself is malformed. In a reality without time before time, asking for a cause assumes a structure that may not exist. Causation requires before and after, requires time. And if time itself emerged with everything else, then asking what came before is like asking what the color blue smells like. The question sounds meaningful but has no answer. The universe may simply be, eternally, necessarily, without cause at all. This is not ignorance dressed as wisdom. This may be the final answer. Not that we failed to find the cause, but that there is no cause to find. The cosmos exists because existence is what reality does, and we are part of that existence. Conscious knots in the fabric, patterns that can contemplate the pattern. We are complexity that arose from simplicity, consciousness that emerged from chaos, observers who can look back at their own origin. This is where I leave you, not with answers but with better questions. The universe is over 13 billion years old, possibly one of countless universes, possibly the only one. We do not know, we may never know, but we are here, made of star stuff, asking questions that stars themselves cannot ask. And there is something beautiful in that. You are not separate from this story. You are the universe knowing itself, the cosmos grown complex enough to wonder about its own birth. Every atom in your body was forged in ancient stellar furnaces. Every thought in your mind is the cosmos thinking. Let that settle over you like starlight. We began with a question. What caused the beginning? We have traveled through time and theory, through temperatures beyond imagination and spaces beyond comprehension. We have met the limits of human knowledge and peered over the edge into the unknown, and we found that some mysteries may be permanent, not failures of science, but features of reality. The wall may not be something we climb, but something that defines the shape of what we can know. Rest now. Let the questions drift. The universe will still be here when you wake, still expanding, still cooling, still holding its secrets in the spaces between stars. You are part of it. That is the answer we can give. Whatever came before, whatever lies beyond, you are here now, aware, wondering, and that is enough. The cosmos breathes, and so do you.